if you have a function, if you have the running time, if you have a running time as a straight line, say this is Tn. How do I more? Okay, let's say this is Tn. We have another function. Like let's say, actually, it's better if I do it in Desmos. If Tn is like 5n or 5x, let's do over 5 instead. So our running time grows like this with every input, our running time goes like this. And let's say there's another function log base 2x. So this function, our running time function, we'll call this tx. Let's call this tn log n gn. Now our running time function will surpass this gn at some point, at this point over here. But even if we multiply gn by a constant, even if we stretch gn, maybe like 5 times gn, let's just do this 5 times gn. Even if we multiply this, at some point tn will still surpass gn. There will always exist, like no matter how much I stretch this gn function, tn will always surpass gn. Now if I have f of n to the power of yeah, let's do n square maybe. $50. Okay, this over here I have another function. At some point this f of n function, sorry, at some point t of n will go below f of n. Like after it surpasses this point, t of n will end up below f of n for all n beyond this point. So we say t n is in the set of O f n. So O, big O is for the upper bound. So this over here is the upper bound, because at some point this will always surpass this. And we also say Tn is in set omega Gn, because Gn is the lower bound. Tn will surpass Gn after some point. After some point, it will remain on top of Gn for all n after it. Now, also one more thing. I have another function h of n which is equal to n minus 2. That's 20. Now Tn will be below Hn. But the thing is, we don't just count we only want the shape of the graph, no matter how stretched it is. So for Gn, no matter how much you stretch Gn, like I multiply this 5, or I multiply this by 6, or I multiply this by 7, no matter how much I stretch it, it will always be below Tn after some point, for all n after some point. Similarly, for Fn over here, no matter how much I stretch it, like instead of 20, it becomes, no matter how much I stretch or squish it, like for 20, and let's do n squared, and let's multiply this by 1 over 20 to 100. Yeah, no matter how much I shrink it, fn is always going to surpass tn at some point. So that's why fn is OFN. OFN means like there's some stretchiness, like there's some value c, after which fn surpasses t at some point, and omega n means there's a, I can shrink the function such that tn surpasses gn after some point. The thing is, now here's the thing. Hn, this black line over here, this is also omega n. T this is also omega n because, sorry, this is also on because hn surpasses tn after some point. Because, but in the definition it says no, if there exists a multiplier, a multiplier in the at the front also counts. So there is always some stretchiness. Like I can stretch this function in a way that this black line surpasses tn. Similarly, I can shrink this function in such a way that the tn surpasses hn. Like over here, for example, let's do 6. Okay, let's just do 10. So tn surpasses hn. There's some constant. I can multiply hn with some constant such that tn surpasses hn. So therefore, tn is also omega hn. If I can multiply the graph by a constant such that tn surpasses it for all points, then for all points after some cutoff point, then it's omega. And if I can multiply the graph by some constant such that hn surpasses tn after some point, then it's omega. Now if it's both big, then it's big O. If it's both big O and omega, then we say it is theta. Theta means there is some constant where it will become the lower bound, and there is also some constant where it will become upper bound. So it's both big O and omega. Tn is in the set omega gn if there exists a positive constant c such that Tn is greater than or equal to cgn for an infinite number of values for n.